Swayam Prabha. Digital India. Educated India.
Welcome to the DTH course on micromachining. Today I am going to talk about a very new process called electrochemical spark micromachining, abbreviated as ECSMM. An overview. Acknowledgement. PhD thesis of Dr. Anjali Kulkarni from IIT Kanpur. MTech thesis of Deepshikha Priyadarshini, again from IIT Kanpur, and MTech thesis of Sanjay Adhikari from IIT Kanpur, and the papers of other researchers from India and abroad. Organization of the talk is as follows: Introduction to electrochemical spark micromachining and setup development, theoretical estimation of temperature in ECSMM process, metrology techniques, ECSMM process performance evaluation, transient current measurement, experimentation and transient temperature measurement, ECSMM process performance evaluation, applications and conclusions. Introduction to ECSMM and development of the setup. Electrochemical spark micromachining is a subtractive process where material is being removed by electrochemical reaction as well as by thermal erosion. Electrochemical spark machining process is an advanced hybrid process which is a combination of ECM and EDM. ECM and EDM are used for machining only electrically conductive materials. They are not used for electrically non-conductive materials, but this hybrid process ECSM and ECSMM can be used for machining both electrically non-conductive materials like glass, ceramics, composites, etc., as well as electrically conductive materials like metals, alloy, etc. It is also being used for machining semiconductors in both meso range as well as micro range. This process can also be used for deposition, that is additive manufacturing process, and selective deposition, micro welding and rapid prototyping of metallic parts can also be done by slightly modifying the process for different purposes. Surface modification has also been done by using this particular process. Working principle of ECSMM process is simple and it can be understood with the help of this particular diagram. Here is electrolytic cell, here is the workpiece which is electrically non-conductive. This is the anode which is much larger in size compared to the cathode, is shown here, which is approximately 50 micron size, and you have the electrolyte which is sodium hydroxide, and you have the supply voltage. It can be pulsed, it can be direct also depending upon your requirement. At cathode, reduction reactions take place. Plating and a hydrogen gas evolution is taking place at cathode over this. 2H2O plus 2E, hydrogen gas is evolved and hydroxides are formed, like this. At anode, dissolution of the workpiece takes place, dissolution takes place, as well as oxygen gas evolution takes place. 4OH plus 2, it results in 2H2O plus oxygen evolution at the anode. So, this is the anode and this is the cathode, but please note it, workpiece is electrically non-conductive. So, it is not the anode as in case of ECM or EDM. Sparking takes place across electrode electrolyte interface, that is the electrode, that is the cathode, and electrolyte is here. So, here sparking is taking place, as you can see shown over here, and always at the smaller electrode, that is also there, because here this electrode is around 50 micron size, while this is much larger than the cathode. So, workpiece is electrically non-conducting, hence it is not anode, as I have mentioned already to you. Material removal mechanism. Momentary high electric field causes the bubble breakdown, because hydrogen bubbles are there, oxygen bubbles are there, and that results in sparking, especially at the smaller size electrode. Number of electrons get generated. The electrons gun or electrons beam impinges on the workpiece, because workpiece is kept very close to the cathode. That is why this spark impinges or this electron beam impinges on the workpiece and material removal takes place. You can see over here, this is the cathode, this is the flow of the electrons, and this is the workpiece which is electrically non-conducting. This is the heated region of the workpiece, and there is a flow of the electrons. It is a sequential phases of ECSM process. One can understand the whole process with the help of this diagram. You have the electrochemical reactions, as I have shown you in the earlier case. Hydrogen gas evolution is there, and bubble formation, water vapor bubble formation is also there. Then you have nucleate pool boiling due to the heated cathode tip is heated for a very high temperature. So, you have the bubble growth causing isolation, and it results in high electric field, sparking takes place across the bubble. Ionization and electron avalanche, and electron drifting towards the workpiece due to potential gradient, and machining due to electron bombardment takes place, because once electrons are bombarding on the workpiece, very high kinetic energy is there, and that high kinetic energy results in the heating and in some cases vaporization of the workpiece material, because the velocity of the electrons is as high as very close to the velocity of the light. So, half mv square, that is kinetic energy, results in heating of the workpiece to a very high temperature. Bombardment of energetic electrons on workpiece is responsible for heat generation, resulting in melting and vaporization of workpiece material. As you can see again here, this is the tool which is cathode, hydrogen bubbles are generated, here is the workpiece which is positive. Electric field of the order of 10⁻⁷ volt per meter is created over there. Note, it is a thermal process assisted by electrochemical reaction. Electrochemical spark micromachining is a thermal process where we have just seen bubbles are generated, and it is assisted by electrochemical reaction, because of which hydrogen and oxygen bubbles are generated. Schematic diagram of experimental setup. It was developed at IIT Kanpur long back, and it was published in the Precision Engineering. You can see here the ECSMM setup. Now, you have the guide support, you have the guide slide mechanism is there which moves it up and down, and it is having the perspex tool holder, and this is the tool, and this is the workpiece, and this is the workpiece support. And here you have the anode, because I have shown you in the earlier slide that anode is kept far away from the cathode. This is the cathode, this is the anode. because workpiece is electrically non-conductive. This is the another sectional view of tabletop machine for drilling cases using the electrochemical spark micromachining. It was developed by Naveen Gautam and Jain in 1998. So, I am not going into details of this, you can look into the paper published by him. Automated electrochemical spark micromachining experimental setup designed and developed at IIT Kanpur by Priyadarshini and Anjali Kulkarni. You can see the photographic view of the same. You can see here different parts are there, and here you can see the workpiece is here and tool is there. I have not indicated separately, but you have the here is the exhaust over the, because fumes are generated and those fumes should be taken out of the chamber and the room where this setup is established. So, you have the very good exhaust over here. This is the power supply. This is the left computer is there for software etc. and controlling the process. This is the power supply over here, and this is the spark generated. So, you can see clearly the spark generation in this particular setup. Different experimental setups developed by different researchers. This is the another setup which was developed by Tandon and Jain in long back, Nejrikar and Jain. With slight modification, these setups have been developed, and Hoffy and Margau they proposed another setup of electrolyte flushing arrangement coaxial with the wire. This is the wire which is using electrochemical spark micromachining process, and electrolyte is being supplied along the axis of the wire, so that it is creating this cavity in this particular workpiece. Here it is coaxial, here it is perpendicular to the wire. So, you can have different kind of the arrangement depending upon the facility and the requirement. Electrolyte flushing arrangement perpendicular to the wire. Types of operations that can be performed using this particular process. Sinking operations can be performed. You move this electrode, means cathode, downward, and this is the workpiece, and due to sparking, as we have already seen, this sinking will take place. This is a travelling wire electrochemical spark micromachining. You have the wire over there, as we have seen in the earlier slide. This can do the cutting of this particular material, removal of this particular material as a solid piece. You can have drilling operation, and you can also have milling operation like this. This is the tool, this is the workpiece using the electrochemical spark micromachining process. And other types of operations can also be performed by proper arrangement of tool and workpiece relative movements, and this is from the chapter by Dr. Binod Yadav. Design and development of experimental setup for ECSMM, another design. Features of the setup: it has 4 axes, 2 micrometer accuracy in XY direction and 50 micrometer accuracy in Z axis, with minimum XY table speed of 10 micrometer per second and tool feed of 10 micrometer per second. Now, this tool feed has very effective role in controlling the accuracy and the material removal rate. We will see it later on. The automation is built using the motion control card on LabVIEW platform. The equipment has the facility of online measurement of process current and gap voltage. This is very important to do the further research in the process, that you are able to measure the current and the voltage online, which can be used for transient analysis of the process. I will discuss in detail about this transient analysis later on. This prototype was developed long back, and it costed around 8 lakhs of rupees to the institute or to the investors. The equipment has been successfully used for micromachining of wide range of materials such as copper, platinum, molybdenum, tungsten, tantalum, etc. All these materials are electrically conductive, but it has also been used for soda lime glass, quartz, etc., which are electrically non-conducting materials. Multifacets is very important feature of this particular process. This setup can be used for micromachining using ECM process, EDM process or ECSM process as we are discussing here. Block diagram of the experimental setup. Some electrical aspects are shown over here. You have the exhaust system, you have the machining chamber, XY table and Z axis control, tool feed and holder, ECS cell, electrochemical sparking cell. You have the control station over here, you have the power supply system. Now, in power supply, you can have the direct current power supply, half wave rectified power supply or pulsating DC supply, and different voltages are used as 5 volt 1 ampere, 12 volt 2 ampere, depending upon your requirement you can select this. The main components of the setup are machining chamber, ECS cell, exhaust system, control of PC and power supply system. For micromachining, train of square pulses and train of triangular pulses are used with variable DC power source. So, different shapes of the pulses, when you are using pulse DC supply, you can use it. We will see the merits and demerits of all these 3 types of pulses little later. Different power sources are used for this purpose. For driving stepper motors, used for XYZ and tool feed, and these are the voltage, current, etc. Time varying process, current and voltage in synchronization by digital storage oscilloscope have been studied in detail. So, you have the voltage, you have the current over here, channel 1, channel 2, and then you have the ECS cell. We will show some of the details of this block diagram of synchronized online measurement scheme for the measurement of online measurement of the temperature and the current. Electrochemical spark micromachining process is a hybrid process, as I have already mentioned. It is a combination of ECM and EDM, and this is the sparking taking place over here by in this particular process. Now, this is very important figure. Now, using this particular process, this 8 or infinity type of the shape has been designed and fabricated at IIT Kanpur, and I will show you the details of this. You can enlarge, magnify this particular part of this shape made by ECSM process. Now, one thing here you can see the outer diameter of this is 2.453 millimeter and inner diameter is 1.558 millimeter. Now, you can see the enlarged view of this particular part, and you can see different defects over here which are really not acceptable. I am deliberately showing this so that you can perform this process under the optimized condition, because the component made like this will not be acceptable on the shop floor. So, I will show you the details of this ECSM process in operation shown over here. You can see the picture over here, 8 shaped microchannel fabricated by this process, and these are the different details of this. Average width of the circle 112 micrometer, that is this width of this circle 112 micrometer. Average width of the heat affected zone 459 micrometer, and average depth of the channel is 140 micrometer. So, these are some of the specifications of this 8 shaped channel fabricated there. Photographic view of experimental setup developed. You can see this is the actual setup which was developed at IIT KA. These are the 3 different types of the thermocouples that were used for the measurement of the temperature, and here is the pyrometer and another 5 channel DSO system is here for studying those waves, etc. Theoretical estimation of temperature in ECSMM process. There are certain assumptions made in theoretical analysis of the process, and these assumptions are very important while you are deriving certain formulation. Temperature at different radii of the workpiece are calculated by considering the spark as a constant circular heat source. This is our assumption, because when you are calculating theoretically, you have to make this assumption whatsoever it is. A single spark takes place at a time. This is again assumption, because experimentally it has also been seen in EDM process as well, that multi spark may take place depending upon the conditions of the tool and workpiece and other machining conditions. The spark is a uniform circular heat source of 5 micrometer diameter. The heat lost to the electrodes is negligible. Again, this is a very important assumption. The thermophysical properties of the material do not change with the temperature. This is another assumption which makes lot of difference or deviation between the theoretical and experimental results, because the material property change with very high temperature. Here temperature may be melting temperature or even vaporization temperature of the material. Temperature of the electrolyte, that is room temperature 294 degree Kelvin. After each spark, the workpiece attains the temperature of the electrolyte. It is another assumption, and you can see here this is discretization of the workpiece that has been done. Here is the surface 2, here is the surface 3, here is the surface 1, and here you can see uniform circular heat source is assumed over here. This is the uniform. In real life or real situation, it may not be like this. It may be a Gaussian, it may be a point heat source also, or some other shape, but for theoretical calculations and simplification, this assumption has been made. And it is also assumed that heat loss due to radiation is neglected. Only heat transfer by conduction and convection are considered. For convection, it is the electrolyte, and for heat transfer by conduction, it is the tool and the workpiece. Boundary conditions and heat equations are like this: minus k d theta over dr is equal to q for r, that is the radius greater than 0 and less than spark radius. So, we have to assume certain spark radius also here, and with q is equal to V I, that is the voltage and current, and V is the supply voltage and I is the current, and 294 degree centigrade is the electrolyte temperature. First element at the center, heat input for the first element at the center, heat input is heat entering the workpiece due to the spark at the circular area on the top surface, and heat going out, heat convected out to the electrolyte through the circular area at the bottom surface, because this workpiece is surrounded by the electrolyte. It is assumed that it is immersed in the electrolyte, and heat conducted out to the next element through the annular area, which we have seen different elements in the earlier slide. I will just show you slides. Different elements are there. These are the different elements which I am saying. Conductor heat is moving from this element to this element, and from this element to the next element. Then for all other elements, heat input is heat conducted in through the annular surface in contact with the previous element, as we have seen in the earlier slide, and heat going out, heat conducted out through the annular area in contact with the next element, plus heat convected, because these elements are surrounded by the electrolyte. So, there will be the heat loss due to the convection also. So, heat convected out to the electrolyte through the surfaces in contact with the elements or same. Now, a set of equations for average temperatures at the center of each element forms a trigonal matrix which is solved by writing a computer program in C language. Comparison of experimentally measured and theoretically estimated results are also performed. Now, here is the temperature controller and this is used, this is the immersion heater is there. So, if temperature goes down below the specified temperature, then this heating will take place, otherwise cooling has to be done. And here is the plate, sodium hydroxide is the electrolyte, all other details are there, thermometer is there, resistance variac etc. are there. Now, temperature distribution on the workpiece we can see, this is pyrometer, T1 point is there, T2 point is there, and you can see these are the experimental results and these are the theoretical results. So, at 180 volt 3%, not much difference is there, but not very large. Same way here also you can see this is the curve, temperature, element number which we have seen earlier, and you can see these are the experimental results, these points, and curve is the theoretical result. So, at some points they are matching very well, at some points there is the deviation, and all these deviations are due to the assumptions made in the evaluation, in the development of the model, theoretical model. And this is another case, 155 volt 5% concentration, and here you can see good matching, but at the middle this matching is not very good, here also it is not very good. Metrology technique for the measurement of the created features. When you are creating micro features, you should know what are the inner dimensions of that feature, and which is very difficult to know by visual eyes or available equipments. So, something was proposed by Dr. Anjali Kulkarni in this particular aspect. Metrology technique used to measure the depth and surface of micro features. The technique is based on replica making using polymeric material. It is effective in quantitative and qualitative analysis of occluded parts, notch like structures and surface topography. I will show you the figure. Process of replica making, it is very simple. First, the fabricated workpiece is cleaned by acetone, then PDMS and harder are mixed in the ratio of 10:1. The solution is poured on the predefined area of the workpiece surface, placed in a plastic box which you have to measure, and then curing is performed by heating in the oven at 85 degrees centigrade for 45 minutes. The liquid solution will solidify. Solidified PDMS is carefully removed from the workpiece. This is very important, it should be removed from the workpiece very carefully. There is no damage, no bending, otherwise the feature that you are going to measure may not be exactly the same as on the real workpiece. This will give the negative replica, I should add the word approximate negative replica of the machine surface with very fine features imprinted on it, because I am using the word approximate because there are so many other things which will make the difference as long as accuracy is concerned. Now, you can see here micro channel is prepared over here, and this is micro dimensions and depth is also in microns, and externally visualize or available setups you cannot measure depth etc. very accurately. So, what was done is that this replica, by pouring that PDMS over here, it solidified and it was taken out and it came like this, and this replica was taken out from here. Now, this replica is magnified and you can see over here this can be magnified replica can be measured under the microscope or by other techniques, and you can see here these are the dimensions: 685 micrometer height here, 715 micrometer, 585 micrometer, 550 micrometer. So, you can measure it closer to each other, and depth as well as the width, so that you can have the idea what kind of micro channel is being produced. Now, this is another one, micro machine surface is there, replica of a complex shaped micro channel showing the machined area surrounded by heat affected zone and surface modification. This is the, you can see here heat affected, this is the area which has been machined, then heat affected zone there, and some surface has been modified over there because of thermal effects. Now, if you enlarge this part, this not this part, this is the enlarged part, this is the enlarged part, then you will find that so many micro cracks are there, and such kind of the surface cannot be accepted in the real life. So, you have to optimize and do further work, so that you get these complex shapes which are acceptable in real life. So, this is the fractal nature of micro machined surface, as you can see here. Now, this is another replica quantized machining zone. These are the another one replicas that have been prepared with the help of the PDMS, and you can analyze their dimensions, width and dimensions under the microscope with magnification. So, what do you infer from here? By using replica molding technique, intricate shapes become easy to visualize from the replica than the actual part in case of cavity or channel. So, this is very clear from earlier slides and this slide, that from actual visualization you cannot make out much, but by this replica technique you can do it better way. Surface modifications and surface topography are easily seen and can be analyzed qualitatively as well as quantitatively. The technique can be standardized, and after resolving the calibration issues, it can be used as a practical approach to the surface metrology on the shop floor. ECSMM process performance evaluation. Machining parameters in ECSMM process are supply voltage, electrolyte concentration, table speed, tool feed and tool workpiece gap, or tool workpiece gap. I cannot call it as inter-electrode gap, because in inter-electrode gap it is the distance between the, or the gap between the tool and the tool is the cathode and there is separate anode. So, that is why we call it as tool workpiece gap. Responses with the help of which performance of this particular process can be evaluated are length, width and depth of the features that you are creating and what you want and what you have obtained. Surface topology or surface roughness, this is another parameter with the help of which you can evaluate the process, and process current. Now, reported work, this reported work was done at IIT Kanpur. ECSMM process performance evaluation, let us see it. Now, there are this is very important slide. I am just going to give you the ideas what has been done and what can be done. You can use direct current, you can use half wave rectified current, you can use alternating current, you can use pulse DC current, and I have told you something about these different types of the currents earlier also. Now, while what we did or what she did really is that using DC, micro holes created for different materials like copper, molybdenum, etc. Parameters that were varied were voltage and tool feed, and responses were hole diameter, microstructure, current, capacitance, and some inferences were made. Using this DC, micro channels were created for different types of materials like soda lime glass, glass pellets, quartz, silicon. These are the electrically non-conducting materials. Parameters were voltage, table speed, sodium hydroxide concentration, and responses were microchannel width, microchannel depth, microstructure current, and some inferences were made. Same things were done with the half wave rectified current, alternating current, and pulsed current. So, we have done it, or she has done it, to study the effect of different types of the power supply on the characteristics of the machine features or micro features on the workpiece, on electrically conducting material as well as electrically non-conducting material. Micro holes on molybdenum under certain machining conditions. You can see this hole was drilled over here, 68.76 micrometer. This is the enlarged view, and you can see the cleanliness and neatness of the hole drilled using this particular process. This is the surface topology. Now, then this is dimple made by this particular process on some other material. Now, you can see the problems also in some cases, that this is the hole really that was wanted, but these are the additional damaged surroundings of this particular hole, maybe thermal effects also. So, dimple region, you can see here what kind of this particular surface is obtained, which is not acceptable. So, you have to use proper type of the tool, I will discuss it later on. So, SEM of hole on tantalum at 8000 magnification. Uniform heat contours are seen all around due to simultaneous heating and quenching. These are the uniform heatings, and the region being given is simultaneous heating as well as cooling, because cooling is taking place simultaneously, because it is immersed under the electrolyte. Microchannel on soda lime glass. This I have shown you already. You can see the enlarged view of this. Now, this is what I want to show, that this is not so good, not goody, because this is the kind of the surface you are going to obtain in real life, and which is not acceptable. It is the SEM image of glass surface. Now, if you further magnify this part, you will see there are micro nano fractures of the workpiece. So, why I am showing it deliberately, that after seeing this, you have to optimize the machining parameters, so that you do not get these kind of the defects on the machine features, otherwise it will not be acceptable to the user. Now, this is another one, microchannels on the glass palette. This is the microchannel of C shape, you can see here. This is the C shape microchannel. The approximate length of each segment in the C type channel is 5000 micrometer. Average width is 535 micrometer and average depth is 370 micrometer. So, you can see all the features that are created on this channel are in terms of microns. Now, important thing to see here is that this is the kind of the surface you are going to obtain by this particular process, and this is not acceptable. So, one has to again analyze it carefully, scientifically, and optimize the parameters, and get that you get really the smooth surface over there. If you further enlarge this, you can see this is the way the material has been removed from here, and this is very rough in that sense, and because these parts may peel off sometime if the forces are acting. So, one has to be careful before really using them in the real products. Simultaneous machining and copper deposition and surface treatment with AC power source. Now, this is again micro fissure created with the help of ECS MMM process. Now, what we are trying to show here is that you see the constituent percentage: oxygen 15, copper 17, silicon 67. So, major part over here is the silicon. Here oxygen 11, this is away from that machine part. This is the machine part, this is the away from that 11, copper 9, here copper was 17 and silicon is 79%. So, silicon percentage is increasing. If you go further, then silicon becomes 98%, and if you go still further 100%. So, what we are trying to show here is that copper is getting deposited over here. Distribution of the elements present in different regions of the section of the microchannel. So, this is the microchannel, and different sections have different constituents, and that was confirmed with this also, EDEX also. So, one conclusion that we can make, that we can use it properly by properly controlling it for copper deposition also in certain area, if that is a requirement. Microchannel on glass using square wave pulsating power source. Now, this is the another example on the glass. that is electrically non-conducting material. Machining in the form of concentric circle is taking place, like you can see over here. Now, this is being shown deliberately, so that in some cases of say EDM process or ECSMM process, people are using Gaussian as the heat source, but here if you see it, it does not look that it is the Gaussian heat source. So, you have to choose the heat source properly, so that your theoretical results are correct and they are better matching with the experimental results. That is why this is being shown here. It is here also, you can see this is the circular one and this is not that way. So, you cannot use the Gaussian heat source. You choose the heat source carefully, keeping this in view. Effect of single spark. So, the crater is of donut type with less machining at the center. This is the center here, here, and maximum machining at the edges of the crater. So, definitely the heat source shape is different than many people assume it. As reverse to the machining with Gaussian type heat source, such observation can be used to decide the type of the heat source being generated, and this will help in your theoretical analysis quite a bit. Now, this is the one which has been proposed by Buttrich et al. In 2005, and this is the shape, micro shape that has been created with by using this particular electrochemical spark micromachining process, and again by the same author, micro hole machined by ECSMM process. You can see nicely produced. These are the blind holes, not the through holes. Now, another important thing which I want to show through this particular slide is that normal assumption is that machining in electrochemical spark micromachining is taking place due to melting and vaporization only, but really speaking it is not so. I will show you here. This is the micro channel machined by using electrochemical spark micromachining, and this is the fractured parts of the quartz. This is not the globule. Globule is here. This is due to the melting of the material and then getting solidified. This is globule here, melting and solidification, but this is the fractured part. So, it simply means that due to the other regions this is happening. So, this confirms the theory that machining of quartz takes place by melting and fracturing, both, not only by melting or melting and vaporization and fracturing. This is the another micro channel, and this is the heat affected zone on both sides. The heat affected zone is the area of base material. This is the base material whose microstructure and properties have altered by welding or heat intensive cutting operations. Now, this is the another one which was again created, this shape by Priyadarshini, if I remember correctly, and S shaped channel with dimension length 3322 micrometer. This length is this, and 844 micrometer is the width. This is the width and this is the length of the channel. Yes, by Deepshika Priyadarshini. Some observations and inferences. SEM of the copper surface treated for less than a second, almost 6 circular zones representing discharge striking on the surface. You can see here, this is the, these are the different zones, circular zones due to the sparking taking place. The smaller circular zones are the result of low energy discharges, and the geometry of single discharge affected zone is circular in nature with an average diameter of 300 micrometer. So, this also indicates that because it is in terms of 300 micrometer or even less than that, so it is very suitable for micromachining purposes. And you have the heat affected zone is almost circular in nature, and it is about 1 millimeter in diameter. So, you can see different zones shown over here. Now, this is another very important part, because composite materials, say glass fiber composite, reinforced composite or other material composite material, they are also being machined and investigated by the researchers in the area of electrochemical spark micromachining. But there are problems when you are machining the composite materials, because the base material has different thermal properties, and fibers that you are using, maybe glass fiber or some other fiber, they have different properties. So, the one which is having lower melting point will get melted out first, and others may not get or may get melted out or vaporized later on. So, that is what we have seen in many cases like this. When Mr. Tandon, if I remember correctly, Mr. Tandon, when he conducted his experiment, this problem was clearly seen. These are the glass fibers, and this is the base material that has melted out, because it has the lower temperature of the melting, while glass fibers had the much higher temperature of the melting. So, one has to be very careful while machining the composite materials. Some observations and inferences. SEM of the copper surface treated for less than a second, almost 6 circular zones representing discharge striking on the surface were observed. As you can see here, these are the geometry of single discharge affected zone is circular in nature with an average diameter of 300 micrometer. You can see over here. Heat affected zone is almost circular in nature, and it is about 1 millimeter in diameter. And this is the problem with composite machining. We can see here composite materials have two constituents, one is the fiber, another is the base material, and both may have different thermal properties. So, the one which is having the lower melting temperature and vaporization temperature, that will get melted out, as you can see over here, and glass fibers, they were having higher melting temperature, and that is why they are remaining there. So, it does not give you very accurate surface machined, and that is why one has to first analyze the process, and before really using it for practical purposes, one has to be careful. Now, some observations and inferences. Here I have already mentioned that it is not only melting and vaporization, rather it is the fracturing also which is responsible for removal of the material in electrochemical spark micromachining, and this is the magnified view of 1 millimeter depth of cut showing the fractured quartz piece shown over here. Now, you can see here the elements that were observed over here. Weight percentage K 16, sorry C carbon 16, oxygen 42%, sodium 2.52, aluminum 1, and silicon 37%. The microanalysis report shows that the major component present is silicon, that is quartz silicon oxide, SiO2, sodium and oxygen are present, as NaOH was used as the electrolyte. It indicates that the material removal is taking place not only by melting, which is represented by the presence of globules, I have shown you there in the earlier slide, and evaporation, but also by mechanical means, that is the fracturing, as I have shown over here. It may be due to repeated heating, due to sparking and cooling due to the presence of electrolyte, that would lead to micro cracks formation and growth due to very high pressure of the electrolyte is there. So, collapse of plasma channel and release of pressure would lead to separation of the fractured quartz like this. Micro hole drilling, and this is important slide. Here we have done the micro drilling micro hole drilling using this particular process. So, you can see here average kerf width is 597 micrometer. These are the different depth of the micro hole that were done, and this is 597 is the average kerf width, 682, 670 769, 821 and so on. And surface finish that is being observed, average surface roughness value is 6.5 micron, 8.15 micron, 7.6 micron, 10.25 and so on. So, one can see that the surface finish is also very poor after electrochemical spark micromachining. So, it requires the proper finishing before really using such kind of the cavities. So, micro hole drilling using ECSM with direct polarity and reverse polarity. So, these minus indicate the direct polarity and this plus indicate the reverse polarity, direct polarity, reverse polarity. We will discuss details of direct polarity and reverse polarity in the next lecture, and Mr. Adhikari has done a lot of work on this interesting aspect of this electrochemical spark micromachining. So, what we have done in this particular not the last lecture, in this particular lecture, introduction to electrochemical spark micromachining and setup development. Setups have been developed by different researchers across the globe. Some of them I have shown here to you here in this particular lecture. Theoretical estimation of temperature in electrochemical spark micromachining process and metrology techniques, and then electrochemical spark micromachining process performance evaluation. Thank you very much. Thank you.